Welcome to day 2 of our 42-day STL Mastery course. Today we are going to unlock two of the most foundational concepts that power the entire standard template library, templates and iterators. These tools help us write generic, reusable and efficient code that does not just work for one type or situation but can be applied across a wide range of scenarios. If you have ever used a vector, map, or stack in C++, you have already benefited from templates and iterators, even if you didn't realize it. So let's explore how they actually work under the hood and how you can yield them with confidence in your own code. Let's take a moment to look at today's learning objectives. First, we will gain a solid understanding of what templates are and why they matter in C++. We will compare function templates to class templates and see where each is used. Next, we will discover how STL is fundamentally built on the idea of templates. Without them, generic containers like vector int or map string int would not exist. Then we will dive into iterators, powerful tools that allow us to navigate through STL containers efficiently. Finally, we will go beyond basic syntax and examine different types of iterators: input, output, forward, bidirectional, and random access. Understanding these categories will make us a more flexible and efficient programmer. So why do we even need templates? Imagine you wanted to write a function that adds two numbers. You could write one for integers, one for floats, another for doubles, but that's not scalable. Templates solve this by enabling generic programming. They allow us to write one version of a function or class that works with any data type, and the compiler generates the type-specific code behind the scenes. This not only reduces code duplication but also improves readability and maintainability. In STL, this is crucial. When you use vector int or vector string, you are actually using the same underlying class template, just instantiated with different data types. Templates are the reason STL containers are so flexible and powerful. Let's start with function templates. Here's a simple template function called add. It accepts two parameters of type t, a placeholder for any data type. When we call this function, the compiler automatically deduces the type based on your input. If you pass integers, it becomes an int function. If you pass floats, it becomes a float function. The result: one function definition, unlimited use cases. This improves consistency, reduces bugs, and is especially useful in competitive programming or system design, where efficiency and clarity are key. Now let's talk about class templates. Class templates follow a similar idea but on a larger scale. They define a blueprint for an entire class that can work with any data type. In this example, we have defined a box class that can store any type t. We can use this class to create a box int, a box double, or even a box string. Class templates are widely used in STL containers. For instance, vector, map, and stack are all class templates. This allows them to store anything, from primitive types to user-defined objects, while maintaining type safety and performance. The entire STL is essentially a massive demonstration of the power of templates. Let's look at a few examples. Vector t stores sequence of any type. Map k, v holds key value pairs of any type combination, and pair t1 t2 bundles two values together. Thanks to templates, STL gives us a set of incredibly versatile tools that work with virtually any data structure or algorithm. We don't need to write separate versions for integers, floats, or strings. We write it once and let the compiler handle the rest. That's not just powerful, it's elegant. Now let's shift our focus to iterators. If containers are like collections of data, then iterators are the navigators that help us move through them. We can think of iterators like smart pointers. They allow us to access elements, move forward or backward, and even manipulate data, all while abstracting away the underlying structure of the container. For example, a vector and a list store data differently, but we can use them the same iterator syntax to loop through them. This uniformity is one of STL's greatest strengths. Iterators aren't one size fits all. In fact, there are 5 main types, each suited for different containers and operations. First, we have input iterators like iStream iterator, which read data one element at a time. Then output iterators like OStream outer iterator, which allow us to write data sequentially. Forward iterators can move in one direction and are used in structures like forward list. Bidirectional iterators, as the name suggests, can go both forward and backward. These are used with list, map, and set. Finally, we have random access iterators, the most powerful type. These support pointer-like operations like indexing and arithmetic. Containers like vector, deque, and array use them. Understanding these types helps us choose the right container and write more optimized code. Here are 2 common ways to iterate over a vector. The first is the traditional method using an iterator object. We declare an iterator, set it to the beginning of the vector, and loop until the end. The second method uses a range-based for loop with the auto keyword. This is cleaner, more modern, and often preferred when we don't need to modify the elements. Both are valid, and choosing one over the other depends on the context. If you are writing older code or working in environments without full C++11 support, you might stick with the classic method. Otherwise, embrace the newer syntax for cleaner and more readable code. Now it's time to apply what we have learned. Try writing a swap function using templates. This will help reinforce the concept of function templates. Next, create a templated class called container T that can store and return any type of value. Practice iterating through a vector and a list using both standard and reverse iterators. And here's a challenge. Reverse a vector without using STL's rbegin or std::reverse. This will test your understanding of both iterators and indexing. Let's summarize what we have covered today. Templates are the backbone of STL. They allow us to write flexible, type-safe, and reusable code. Function and class templates simplify our code base and make it easier to maintain. Iterators provide a unified way to access elements in STL containers, regardless of their internal structure. And lastly, knowing the different types of iterators helps us optimize our code and choose the right approach for every problem. Want to go a little deeper? Explore iterator triads, which are used to determine iterator category and properties at compile time. Try creating your own custom iterator class for a data structure. It's a great way to understand how STL does it behind the scene. Also learn about iterator invalidation, which occurs when changes to a container make existing iterators invalid or unsafe to use. This is especially important in competitive coding and interviews. To reinforce today's concepts, here's your assignment. Write a function template max of 3 to find the largest of 3 values. Build a class point t with a member function to calculate distance between 2 points. This is a great way to use class templates practically. Traverse both a deque and a list using iterators, forward and reverse. And finally, take on the bonus challenge. Reverse a vector without using built-in STL methods like rbegin or reverse. This assignment will not only test your understanding but also prepare you for more complex topics ahead.